There's a widespread misconception about how physics works, and it has to do with intelligence. People think that to be a good physicist, you need to be extraordinarily smart. You need a high IQ. You need to be able to hold complicated mathematical structures in your head. You need to think faster than everyone else. This is wrong, completely wrong. And I can prove it to you by examining how actual physics gets done and what actually matters when you're trying to understand nature. Let me start with something concrete. When I was at Los Alamos during the war working on the atomic bomb project, I met some of the smartest people in the world. Hans Bethe, Enrico Fermi, John von Neumann, Niels Bohr. These were giants of physics. Von Neumann, in particular, had a reputation for being the smartest person anyone had ever met. He could multiply large numbers in his head instantly. He had a photographic memory. He could follow the most abstract mathematical arguments without writing anything down. And yet when it came to solving actual physics problems where you had to figure out what nature was really doing, von Neumann wasn't necessarily faster or better than the rest of us. Sometimes he was slower. Why? Because being smart in that conventional sense, having a high IQ, being quick with mathematics, doesn't directly translate to understanding physics. Here, quote, "That's what I mean. Physics isn't about manipulating symbols on paper according to rules. That's mathematics. And yes, you need mathematics to do physics, but physics is about understanding what's actually happening in the physical world. It's about developing intuition for how nature behaves, and that requires something different from raw intelligence." Let me give you an example. One day at Los Alamos, we were trying to calculate something about the implosion mechanism of the bomb. The calculation was complicated, involving shock waves, hydrodynamics, equations of state for materials under extreme pressure. Von Neumann could do the mathematical manipulations faster than anyone, but Fermi would sit there, thinking, and he'd say something like, "Well, the pressure should be roughly this, and the temperature should be roughly that, and here's why." And he'd be right. Not exactly right, but close enough that when you did the detailed calculation, it confirmed his rough estimate. How did Fermi do this? He wasn't doing the full calculation in his head. That's impossible. He was using physical intuition. He understood how things scaled, what the important factors were, what could be ignored. He could feel his way through a problem. This is a completely different skill from being able to manipulate equations quickly. Or consider Einstein. When Einstein developed special relativity, he didn't do it by being mathematically clever. He did it by thinking very carefully about what it meant to measure time and space, about what simultaneity meant, about how light behaved. He took these simple, clear ideas and followed their implications rigorously. The mathematics wasn't complicated. A good high school student can follow the mathematics of special relativity. What was brilliant was the clarity of thought, the willingness to question assumptions that everyone else took for granted. Here, quotes another case. Dirac, one of the greatest physicists of the 20th century, developed his equation for the electron by combining quantum mechanics with special relativity. The equation is mathematically beautiful, and it predicted the existence of antimatter. But if you read how Dirac thought about physics, he wasn't trying to be clever, he was trying to be clear. He was looking for the simplest, most elegant mathematical structure that could describe the electron. He trusted in beauty and simplicity. Now, you might say, well, all these people were still very intelligent. And that's true. You can't do physics if you're unable to follow mathematical arguments or unable to think logically. But there's a crucial difference between having enough intelligence to do physics and having the highest possible IQ. Beyond a certain threshold, and that threshold isn't as high as people think, more raw intelligence doesn't help much. What matters is how you think, not how fast you think. Let me tell you about my own experience. When I took IQ tests, I scored around 125. That's above average, but it's not genius level. It's not von Neumann, and yet I was able to contribute to physics. I worked on quantum electrodynamics, developed path integrals, contributed to understanding liquid helium, worked on weak interactions, taught thousands of students. How? Not by being the smartest person in the room, but by thinking about problems in the right way. What's the right way? First, you have to really understand the problem. Not just memorize the equations, but understand what they mean physically. When you write down Phi equals ma, you need to know that this is telling you that force causes acceleration, that heavier objects are harder to accelerate, that acceleration is a change in velocity. These seem obvious, but many students memorize the equation without understanding what it's saying about the world. Second, you have to break complicated problems into simple pieces. Every hard problem in physics is really a collection of easier problems stacked together. If you can identify the pieces and solve them one at a time, you can solve the whole thing. This doesn't require genius. It requires patience and clear thinking. Third, you have to check your work constantly. Does this answer make physical sense? If I calculated that an electron is moving faster than light, I made a mistake somewhere. If I calculated that a tiny magnet produces more energy than the sun, something went wrong. You use your physical intuition to catch errors, and you develop that intuition by solving lots of problems and thinking carefully about what the answers mean. Fourth comma, and this is crucial, you have to be willing to not understand something for a while. Some people, especially people who pride themselves on being smart, can't tolerate confusion. They need to feel like they understand everything immediately. But physics doesn't work like that. Sometimes you have to sit with a problem, try different approaches, make mistakes, get confused, and slowly work your way toward understanding. If you need to feel smart all the time, you'll give up before you get there. Let me make this concrete with how I approached quantum electrodynamics. The problem was that when you tried to calculate the interaction of an electron with light, you got infinities. The theory seemed broken. Very smart people had worked on this for years and couldn't solve it. Bethe, Schwinger, Tomonaga were all attacking the problem. I didn't try to be smarter than them. Instead, I went back to basics. I asked what is actually happening when an electron interacts with a photon. I drew pictures, space-time diagrams showing the electron path, the photon path where they meet. These diagrams weren't mathematically sophisticated. They were just pictures, but they helped me think clearly about the physics. Then I remembered something from classical mechanics, the principle of least action. You can describe a particle's motion not by tracking forces at every instant, but by considering all possible paths and finding the one that minimizes the action. This is just a different way of formulating Newton's laws, but it's conceptually cleaner. I thought, what if I apply this to quantum mechanics? What if, instead of picking the one path with minimum action, I sum over all paths with quantum amplitudes? Each path contributes an amplitude proportional to e to the I times the action. This wasn't a brilliant leap. It was a simple idea. Take a classical principle and quantize it in the most straightforward way possible. But this simple idea turned out to be powerful. It gave me a way to visualize quantum processes and calculate them systematically. The diagrams made the calculations easier because you could see what was happening. And the infinities could be handled by a procedure called renormalization, where you absorb them into redefinitions of mass and charge. Was this genius? I don't think so. It was careful, systematic thinking. I took existing ideas, the action principle, quantum mechanics, perturbation theory, and combined them in a natural way. The key wasn't being super smart. The key was thinking clearly and not giving up when things got confusing. Here's what I've learned about intelligence and physics. There are roughly 3 levels of intelligence. Below a certain level, you simply can't do physics. You can't follow the mathematical arguments. You can't see the logical connections. You can't hold the structure of a theory in your mind. This level is probably around IQ 100 to 110. Most people are at or above this level. Above that threshold, up to maybe IQ 130 or 140, more intelligence helps. You can follow arguments more easily, learn mathematics faster, see connections between ideas more readily. This makes learning physics easier and faster. If you're in this range, you can definitely become a good physicist if you work hard and think carefully. But above that level, above 140 or 150, I'm not convinced more intelligence helps much at all. Von Neumann could calculate faster than me, but that didn't make him better at physics. What matters at this level isn't raw processing power. It's creativity, intuition, the ability to see problems from new angles, the persistence to work on something for years without giving up. And here's the trap. If you're very intelligent in the conventional sense, you might rely too much on that intelligence. You might try to solve problems by being clever rather than by understanding them deeply. You might get impatient with the slow, careful work of building physical intuition. You might avoid problems that don't yield to quick, clever tricks. I've seen this happen. Very smart students come to physics. They breeze through the early courses because they can manipulate equations quickly, and then they hit something really hard, maybe quantum field theory, maybe general relativity, and suddenly being clever isn't enough. They need to develop intuition. They need to sit with confusion. They need to work through lots of examples, but they never learned how to do this because they never needed to before. They relied on being smart, and now being smart isn't enough, and they don't have the other skills. Meanwhile, students who weren't quite as quick, but who learned early on that they needed to really understand things, that they needed to work through problems carefully, that they needed to develop physical intuition, these students often do better. They have the right habits of thought. Let me tell you about teaching. I've taught thousands of students at Caltech. The students who succeed aren't always the ones who seem smartest at first. They're the ones who ask the right questions. What does this equation mean physically? Why does this approximation work here? How do I know when this formula applies? These questions show that the student is trying to understand, not just memorize. The students who struggle are often the ones who try to memorize everything, who think physics is about knowing lots of formulas, or the ones who try to be too clever, who jump to conclusions without working through the steps, or the ones who are afraid to admit confusion, who pretend they understand when they don't. Intelligence can actually make these traps worse. If you're smart enough to fool yourself into thinking you understand something when you don't, that's dangerous. If you're smart enough to come up with clever-sounding explanations that are actually wrong, that's a problem. If you're so used to being right that you can't handle being wrong, you'll never learn. Here's a specific example. In quantum mechanics, there's the uncertainty principle. Position and momentum can't both be known precisely. Many students memorize this as delta x times delta p is greater than or equal to h bar over 2. They can plug numbers into this formula. But do they understand why this is true? The deep reason has to do with the wave nature of matter. If you want to know the position precisely, you need a wave packet that's very localized in space. But a localized wave packet is a superposition of many different momentum states. So the momentum is uncertain. Conversely, a state with definite momentum is a plane wave which is spread out over all space, so position is uncertain. The uncertainty principle isn't a statement about measurement or disturbance. It's a statement about the intrinsic nature of quantum states. A smart student can memorize the formula and use it correctly, but that doesn't mean they understand it. Understanding requires something deeper. You need to be able to explain it in different ways, to see how it connects to other concepts, to apply it to new situations, to recognize when it's relevant and when it's not. This kind of understanding doesn't come from intelligence. It comes from thinking carefully and repeatedly about the concept until it becomes clear. I quote Farr also noticed that very intelligent people sometimes have trouble communicating their ideas. They can see connections and implications quickly, and they assume everyone else can too. They skip steps in their reasoning because those steps seem obvious to them. But teaching requires slowing down, making every step explicit, checking that your audience is following. This is actually harder for very smart people because they have to constantly suppress their instinct to jump ahead. When I teach, I try to explain things as simply as possible, not by dumbing them down, but by finding the clearest, most direct path to understanding. This means stripping away unnecessary complications, focusing on the essential physics, using concrete examples. Very smart people sometimes resist this because it feels too simple. They want to show off their sophistication, but simple explanations are usually better explanations. Here, quote, another trap that high intelligence creates. If you're very smart, people expect a lot from you. They expect you to have brilliant insights, to solve problems others can't solve, to be right more often than everyone else. This creates pressure, and under this pressure, some people start to fake it. They pretend to understand things they don't. They offer confident opinions on topics they haven't thought through carefully. They're more concerned with appearing smart than with actually understanding. This is deadly in science. Science requires honesty, especially honesty with yourself. You have to be willing to say, I don't know. You have to be willing to admit when you're confused. You have to be willing to consider the possibility that you're wrong. If you're too invested in being the smart person, you can't do this. I quote, tried to cultivate the opposite attitude. I'm happy to say I don't know. I'm happy to admit confusion. I'm happy to make mistakes in public, because that's how you learn. When I was younger, this sometimes bothered people. They expected me to have all the answers because I was a professor at Caltech, because I'd won awards. But I didn't have all the answers. Nobody does. And pretending otherwise is dishonest. Let me tell you about playing bongos. People sometimes found it strange that I played bongos in my spare time. What does that have to do with physics? Nothing directly, but it had to do with thinking. When I played bongos, I wasn't trying to be good. I wasn't competing with professional musicians. I was just exploring, experimenting, seeing what sounds I could make. This is exactly the attitude you need in physics. You explore, you experiment. You're not afraid to make noise that doesn't sound good. Or consider lockpicking. Another hobby I had. People thought this was frivolous. But lockpicking teaches you to pay attention to tiny details, to develop a feel for mechanical systems, to persist when something doesn't work immediately. These are exactly the skills you need in physics. You're trying to figure out how nature works, and nature doesn't give up her secrets easily. You have to be patient, you have to pay attention, you have to try different approaches. The point is, being a physicist isn't about being smart in some narrow, conventional sense. It's about curiosity, persistence, honesty, clear thinking, physical intuition. These qualities aren't strongly correlated with IQ beyond a basic threshold. You can cultivate them through practice, through solving lots of problems, through thinking carefully about what equations mean, through being honest about what you do and don't understand. Now, let me address something that might be bothering you. If intelligence isn't the key to doing physics, why are most physicists intelligent? The answer is selection. To become a physicist, you have to get through a lot of education. You have to pass tests, solve problem sets, write papers. People with higher intelligence find this easier, so they're more likely to persist. But this doesn't mean that the intelligence itself is what makes them good at physics. It just means they're more likely to stick with it long enough to develop the real skills that matter. There's also a cultural factor. Physics has a reputation as being for very smart people. This attracts people who want to prove they're smart, but these aren't necessarily the people who will do the best physics. Sometimes the best physicists are the ones who aren't trying to prove anything. They just genuinely want to understand how nature works. I quote, known several physicists who weren't considered particularly brilliant by their peers, but who made important contributions because they were willing to work on unfashionable problems, or because they developed deep expertise in some specific area, or because they thought very carefully about issues that others glossed over. Steady, persistent work often beats brilliant flashes of insight. Here's a concrete recommendation. If you want to be good at physics, don't try to be smart. Instead, try to be clear. When you read a physics textbook or paper, don't just follow the mathematics. Stop at every step and ask yourself, what does this mean physically? Why is this step valid? Could I explain this to someone else? If you can't answer these questions, you don't really understand yet. No matter how well you can follow the equations, work through lots of examples. Do the problem sets, even if they're not required. Make up your own problems. Take a concept and apply it to different situations until you really understand how it works. This is slow, hard work. It's not glamorous, but it's how you develop physical intuition. Don't be afraid to use simple models. If you're trying to understand something complicated, start with the simplest version of the problem. Ignore things that seem like details. Get the basic physics right first, then add complications. Very smart people sometimes resist this because they want to solve the full problem right away. But that's usually a mistake. You understand the full problem better if you've worked through the simple version first. Talk to other people about physics. Explain your understanding to someone else. When you have to put your ideas into words, you discover gaps in your understanding. You realize what you don't really know. This is valuable, and discussing physics with others exposes you to different ways of thinking about problems. Read original papers, not just textbooks. Textbooks present polished, cleaned-up versions of theories. Original papers show you how the ideas actually developed. They show the false starts, the confusions, the gradual process of figuring things out. This is more realistic than the textbook version where everything seems inevitable and obvious. Be patient with yourself. Nobody understands everything immediately. Dirac once said that in physics you should understand things in different ways, and you keep working until they all fit together. This takes time. If you're confused about something, that's normal. Stay with it. Keep thinking about it from different angles. Eventually things click into place. Now, here's the deepest point I want to make. The reason high IQ can be a trap isn't just that it doesn't help as much as people think. It's that it can actively interfere with the kind of thinking physics requires. Physics requires humility. Nature is smarter than you are. Nature doesn't care about your elegant theories or your clever mathematics. Nature does what it does, and your job is to figure out what that is. If you're very intelligent and you've been praised for your intelligence your whole life, humility doesn't come naturally. You're used to being right. You're used to figuring things out quickly. You're used to impressing people with your insights. But in physics, you're going to be wrong a lot. Your first approach to a problem probably won't work. Your intuition will mislead you. Nature will surprise you. This is okay. This is how science works. But if you can't tolerate being wrong, if you can't handle confusion and uncertainty, you'll struggle. And paradoxically, very smart people sometimes struggle more with this because they're not used to it. I've spent my entire career being confused about things. I'm confused about quantum mechanics, not the mathematics, which I understand fine, but what it means about reality. I'm confused about consciousness. I'm confused about why the universe has the laws it has. These confusions don't go away. You live with them. You keep thinking about them. Maybe someday you'll understand. Maybe you won't. But the confusion itself isn't a failure. It's an honest recognition that these are hard problems. Very smart people sometimes can't admit confusion because it threatens their self-image. They're supposed to be the smart one who understands things, so they convince themselves they understand when they don't. They generate pseudo-explanations that sound good but don't actually explain anything. This is worse than admitting ignorance because now you're fooling yourself. Let me give you one final example that ties this together. When I was working on the Challenger disaster investigation, I had to figure out why the space shuttle exploded. There were a lot of very smart engineers and administrators involved. Some of them were telling complicated stories about ice formation and erosion and all sorts of technical details. But something felt wrong to me. I got a sample of the O-ring material that seals the joints between rocket segments. I put it in ice water to cool it down. Then I took it out and showed that when it was cold, it lost its resilience. It didn't spring back the way it should. This was a simple experiment. Any high school student could have done it, but it showed the fundamental problem. When the shuttle launched on a cold morning, the O-rings were too stiff to seal properly, and hot gases leaked through and caused the explosion. The point isn't that I was smarter than everyone else. The point is that I did a simple direct test of the key question: do the O-rings work when it's cold? I didn't get lost in complicated analyses. I went straight to the physics, and that's what physics is about. Not being clever, but asking the right question and finding the simplest way to answer it. So here's my message. If you want to understand physics, don't worry about being smart. Focus on being clear, being honest, being persistent. Develop physical intuition by working through lots of problems. Check your understanding by explaining things to others. Be willing to be confused and work through that confusion slowly and carefully. These are the skills that matter. Intelligence helps. Yes, but beyond a basic level, it's not the limiting factor. The limiting factors are clarity of thought, physical intuition, persistence, and honesty with yourself. These aren't gifts you're born with. They're skills you develop through practice. Anyone with reasonable intelligence and willingness to work hard can develop them. That's the real message. Physics isn't a genius game. It's a craft. And like any craft, you get better at it by practicing, by making mistakes and learning from them, by gradually building up your skills and intuition. Stop trying to be smart. Start trying to understand. That's how physics actually works.